All right, let's get started. Good afternoon, everybody. Welcome. So I'm pleased to welcome today's speaker. It's George Domat from University of Utah. And before passing the microphone to him, let me remind everybody that once the speaker starts talking, I'd like to ask everyone to please put yourself on mute. And when and if you want to ask a question, please unmute yourself and ask a question. So after the talk, as usual, you don't have to disappear right away. There will be a period of informal chat and discussion after the recording is turned off, so you can stay and talk to each other. And with that said, I'm once again pleased to welcome today's speaker, George Domat, and he's going to tell us something about free products from what is it?
Spinning
rotating families. Yeah.
Great, thank you. Before I start, I want to thank Ilya and the other organizers for inviting me, and also to all of you for coming. So yeah, I want to tell you about free products from spinning and rotating families. And I guess I should say, clearly my handwriting is not the best, so if something is illegible, please ask me. And that also just goes for everything. I want this talk to be pretty accessible, so feel free to just unmute yourself and yell out if you have any questions. Also, sometimes my microphone doesn't pick me up when I'm writing and looking down. So if anything ever gets quiet, also somebody let me know, please. Great. So this all is joint work together with Mladen Besvina, Ryan Dickman, Sang-Hoon Kwok, Prem Patel, and Emily Stark. And so to kind of start and to give a motivation of where all this work comes from, it comes from kind of some ideas from Basser theory. And so, okay, Basser theory is pretty broad, but there's this theorem that you can get, which is not the full power of Basser theory, but this is kind of setting that I care about, is you suppose that you have a group acting on a tree and say that it acts without edge inversions and with trivial edge stabilizers. And suppose even more that your group is generated by all of the vertex stabilizers. So then what does Basser theory tell you? It lets you kind of say something about the structure of the group. And in this specific setting, it tells you that the group is equal to just a free product over the vertex stabilizers. So it's not quite over all, it's over some subset of the vertices. And really this is, you pick a representative in each orbit, but so it tells you, you take this action on a tree with some nice properties and it gives you this free product structure. Great. So let's kind of talk through this in an example. So let's consider the infinite dihedral group. So here's a presentation for it. It has two generators. One is order 2, one is infinite order. It's the difference between the infinite dihedral group and a finite dihedral group. And so this group, it acts on a tree. And what tree does it act on? Well, it just acts on the real line. And we can turn this into a tree by just putting vertices at all the integer points and then edges between. Okay, and how does it act? Well, it has two generators. Let me just tell you how they work. So S of x is going to take it to minus x. So this is just going to kind of flip the whole thing about the origin. And then R is just going to act by translation. So R will just translate by 1. Great. Okay, so now we have an action on a tree. Okay, there's one thing we have to do. So I said we want an action without edge inversions. So right now there are edge inversions because S flips these two edges. But we can kind of eliminate that by subdividing the tree. So let's just subdivide it each edge. So now you won't flip any of the edges. Great. So now kind of what does Basser theory let you do? Well, let's consider the quotient graph by this action. Or kind of alternatively, you can just think of a fundamental domain of the action. So what is this going to have? It's going to have two vertices. One collection is going to be kind of all the original integer points. And the other collection is going to be these new subdivision points. Okay, and this graph will also only have one edge. Oops. So you can see that all of these edges get taken to each other, right? So the kind of translation, we'll take this edge to this, well, maybe I shouldn't use green. We'll take this edge to this edge to this edge, etc. And then if you flip, you'll get the other set of edges. So we have only one edge. Okay, but let's also kind of look at what are the vertex stabilizers and the edge stabilizers here. So for this purple point, like this is going to be stabilized by the group generated by S, which is just a Z mod 2Z. And this green, right, it takes a second to think about what it gets stabilized by, but one thing it does is you can flip by S and then push by R. So that will stabilize that one. And okay, here I'm just picking a representative for these points. So this is stabilized by the group generated by RS, which you can check is also a Z mod 2Z. And okay, the edges are going to have trivial edge stabilizers. Every element will move an edge off itself. So this is what is called a graph of groups. And I also want to note, so D infinity is in fact generated by these two groups. So these two elements are generators for D infinity. Okay, so now what's the glory of adversary theory is you have this action, right? And now we know that D infinity is generated by these two elements, and we want to say something about the structure. And how do you do that? You kind of take this graph of groups and you blow it up to a graph of spaces. So what we're going to do is we're going to replace each vertex with a KG1 for the group. And then just use regular old Van Kampen to see what this group is. So you get a graph of spaces. And so what do? We just blow up each vertex into its KG1. And what is that? That's just RP infinity here. Okay, and because this edge stabilizer is trivial, well, it just stays an edge. Okay, and so now if we take the fundamental group of this thing, well, that's the same thing as the group generated by S and RS. And you can just use Van Kampen to see that, okay, what is this? It's Z mod 2Z, free product, Z mod 2Z. Okay, but we said this is also D infinity, because D infinity is generated by these two elements. So this is how we see that we can kind of use this action on a tree to kind of decompose your group as a free product. And this is kind of going to be the running theme of this whole talk, is how to generalize this. If you really like the tree picture, you can take this graph of spaces and lift it to its universal cover. Oops. And really kind of recover the tree, where now you take a little universal cover of each of the RP infinities. And you see you get kind of a line of these spheres. So in some sense, you can see the tree being recovered. Great. Any questions on that? Great. So now I want to talk about some generalizations that have happened in the past couple of years. And I'm not going to state any theorems of Gromov, but it all does build on work of Gromov. He introduced a lot of the objects here. I've heard that if you give a talk in geometric group theory, you always need to reference Gromov. Well, here I am, but it's not just a kind of mandatory one. He truly did come up with some of the ideas behind these theorems. Great. So the first theorem is due to Domani, Girardel-Osen. And what does it say? So it generalizes this theorem above to an action on a delta hyperbolic space. And so what does it say? It says that if you have a group acting on a delta hyperbolic geodesic metric space, and you have this family, and what is this family curly C? It's some subset of X, so just some subset of points. And then associated to each point, you have a group. And this group is a subgroup of the stabilizer of that point. So this is going to be our vertex stabilizers here. And okay, this collection needs to satisfy some conditions. It needs to be row separated. What does that mean? It just means all the points in C are separated by row. And it needs to be very rotating. And I'll give kind of a strict definition later, but I'll give some intuition in a second about what that means. But that's some condition on these groups, GC, and how they act. And so if this is true for some big enough row, then what is true? Then you take the normal closure now of this set of vertex stabilizers. I'm doing this in quotes because they're not exactly the full stabilizers, but they're subgroups. And well, then the normal closure of this is isomorphic to a free product of these groups. Again, for some subset. Great. And so what does this kind of look like pictorially? so you have your space X, and you have this very separated collection of points. And now, kind of at each one of these points, you have a little group that acts and fixes that point. Okay, now what does the very rotating say? It says that, okay, if you take something in one of these groups, G, let's say take little g and GA, well, then if you apply it to C, well, that's going to get, first, what is part of the rotating? It says that this family C is equivariant under all these groups. Okay, so now if you do this, you take C and you move it somewhere else, and you're fixing A. Well, the very rotating condition says that, okay, well, then if you draw the geodesic between C and GC, it has to go through A. So in some sense, you can kind of see this, you kind of have to rotate about A. And so if this is true for kind of all of these groups at all these points, well, then what does this theorem say? It just says that, okay, now if you look at the normal closure of this group, this is actually just a free product over, okay, some of these things. And again, sum just means you take like a representative of the orders. Great, and I want to, one thing I want to point out is you can kind of almost already start to see the tree-like structure when you have this very rotating, right? If you could kind of draw the geodesics between these points, you could maybe imagine that it kind of creates some sort of tree-like structure. Okay. Any question about the statement of that one? Okay, and then the other kind of new result is due to Clay, Mangas, and Margalit. And what do they say? Okay, well, now the setting's different. Now the setting is not acting on a delta hyperbolic space, it's acting on a projection complex. And I won't tell you right now what that is, but later I'll get into that. But it's just, okay, you have a group acting on now some new type of space with pretty much the same setup. So again, you have these GCs. So I guess the one thing I should say is this projection complex is a graph. So these GCs are, again, just subgroups of the stabilizers. And you have this for every vertex in the graph. And here, the condition you need is to be an equivariant L spinning family. So equivariant just means they're equivariant with respect to the group. L spinning is some analogous thing as rotating. And so if this L is big enough, then we get the same exact result. Then if you take the normal closure in G of all these subgroups, then it's isomorphic to a free product over these groups. Great, and here kind of what's the picture? It's very similar. So here your projection complex is a graph. It's not quite a tree, but it actually will turn out to be a quasi-tree. And so now, like associated to each vertex, say A, you have some group acting GA that fixes it. And now if you take some other vertex B, and you look at GB, where G is something in GA, well, what do we get? It turns out part of the information of a projection complex is you have some notion of kind of angle almost, or you have some notion of the distance with respect to A between 2 points. So what you do is it says that, okay, now there's some distance defined here, and this distance is big. And if this is true everywhere, you get the same conclusion. Now, if you take the group generated by all of these GCs, this is the free product, again, over some subset. Great. So these are kind of very far-reaching theorems. They have a lot of applications. So they have applications, kind of the original applications into mapping class groups, to out-offend certain classes of relatively hyperbolic groups. Here I've stated a theorem due to DGO that kind of gives an example of the type of application. So if you have a closed orientable surface, then there's some number such that if you take any pseudo-Nosov element in the mapping class group, then the normal closure of A to the n is free and purely pseudo-Nosov. Yeah, this is also true in out-offend, where you replace pseudo-Nosov with EWIP. And you can also prove that in other types of theorems. The CMM, they did more things like partial pseudo-Nosovs on surfaces and saw that you got rags. But I'm not really going to talk about these applications. I just kind of want to point out that they exist and there are a lot of them. And a lot of them kind of answered some old open questions due to Ivanov and various other people in the mapping class group setting. So these are kind of powerful theorems. Great. So now what do we do, right? I've now only talked about other people's theorems. But what do we do? Well, what we do is we unify these two theorems. right? I mean, they look very similar. And really, what do? We see that, okay, this Clay-Mangas-Margulies theorem actually implies the Dgo theorem, the Domat-Gödel-Osen theorem. And so what this does is it simplifies the proof of the Dgo theorem, right? This is kind of, this theorem is part of this long kind of 150-page paper, it's now kind of book of Dgo. And so we kind of wanted to write a kind of self-contained shorter proof of it. Okay, the whole 150 pages is not dedicated to this theorem, but it is in there, and I think it's difficult. And so what we do is kind of simplify it a bit. And okay, also for the sake of kind of being self-contained, we also give a new proof of the CMM theorem. Great. So what does our theorem say? And it might not mean that much right now, but I kind of want to state it, and then later on I'll make sure everything gets defined. But basically what it says, before I beat out the whole thing, it says that if you have the setup of Dgo, well, then you can transform it into being in the setup of CMM. And so then if you get there, then you just directly apply the CMM theorem and you get the result that you want. So what is the setup? It's you start with the Dgo setup, which is a group acting on delta hyperbolic space with this rotating family. Okay, then the first thing we prove is, okay, now with this setup, you can build an action on a projection complex. And then if you do have this fairly, okay, here we say fairly rotating. Oops. Before I said very rotating, this is just a slightly weaker condition. I'm not really going to worry about the difference, but it's strictly weaker than the Dgo hypotheses. So if you have this fairly rotating, well, then you get an L spinning family. And I guess one thing I want to point out, here I wrote metric graph. This is also not necessary. The full strength of Dgo is just for metric space, geodesic metric space. But for the sake of exposition, we just did everything for graphs. And then there's a, we can prove the little lemma that says you can upgrade something to a graph. Great. So with this theorem, this theorem kind of plus the Clay-Mangas-Margulies result implies the Dgo result. Great. So kind of this is what I'm going to focus most of the talk on, and hopefully at the end I'll have 5 minutes to say a word about our new proof of CMM, at least to say just kind of what is the new piece that we do that's different. But I really want to focus on this theorem. So I'll pause now. Any questions? Great. So now the first thing I'm going to do is I've kind of promised this to you, is I need to define projection complexes. So this is kind of the main tool. And this construction is due to Vespina, Bromberg, and Fujiwara. And then there's a slightly more recent paper with them and Alex Sisto that simplifies some of the machinery. And so what is this? What's the starting point? Well, the starting point is you just have some set, just a set y, curly y. And now for each point in this set, you have a distance function for that point. And so the distance function is on all the other points in the set. So what does this look like? So I like to imagine this as kind of each thing is a little piece. And so how does this distance function work? It says that, okay, well, if I'm standing on y, I can measure, I can measure the distance between x and z from the perspective of y. So one way to think about this is I can kind of project x down, and I can project z down. And now I can measure some distance between x and z. Another way I like to think about this is, okay, this curly set y is this collection of planets. And if you're standing on one planet y, okay, well, now you can kind of measure the distance between two other ones by kind of looking in the night sky and seeing how far you have to move your head. So something's really far apart is if you're standing on y and you have to look here on the horizon to see x, and then you kind of turn all the way around and see z behind you. Great. And so now what's the goal of this is you start with this setup and you want to use this information, right? For now, y is just a set. It has no structure. You just want to use this information to turn y into a kind of nice graph. Right, so in applications, you'll have some group acting on a set that kind of respects these distances. And now you want to build kind of a geometric object for it to act on. Okay, so this isn't going to work in general. You're going to need to satisfy some axioms. And what are these? So they're all going to be kind of with respect to some constant that we're just going to carry around with us, some projection constant. What do these first two say? These first two say that, okay, these dy's, they're just actually distance functions. Right, this first one's just saying they're symmetric. The next one's saying triangle inequality. These look innocuous, but actually turns out triangle inequality gave us the most issue in our application. But and then this next one, P1, this is also kind of a distance function-y thing. You know, these aren't strictly metrics, right? dy of x to x is not necessarily 0, but it has to be bounded. Right, just data. Okay, the next two are kind of the more interesting ones. So this one, what does this say? This says that if you have a large projection, so if you stand on y and you see a large distance between x and z, well, then if you fly over to x, you see a small distance between y and z. And why is this important? It gives you a notion of betweenness. Right, so we kind of say that y is between x and z if it measures a large distance between them. And okay, this is, in other languages, this is the Baerstock inequality when you're in the setting of surfaces and subsurface projections. So a lot of this, these definitions kind of are inspired by the Maser-Minsky machinery for subsurface projections. And so this, in that setting, is exactly the Baerstock inequality. But kind of what does this look like pictorially, right? I mean, you have your y, and now you have x over here, and this is kind of the projection of x to y, and then you have a z over here, and it projects here. Okay, well, if these are very far apart on y, well, then when you look over on x, if you're standing on x, these have to look very close together. So I've drawn this picture kind of, suggestively. I mean, y is sitting kind of between x and z. That's really what this means. Great, and then there's one more axiom. And this says that if you pick any two, x and z, and you count the number of y's that are between x and z, so what does that mean? That means you count the number of things that measure a large distance between them. This has to be finite. So this is telling you there's only finitely many points between any two. Right, and this is good because we want to define a graph structure, right? And so you don't want things infinitely far apart. Great. Any questions on these? Hey, now you might say, wait a minute, like what? These are okay. These are some things you can define, but does anything actually satisfy them? What are examples of things that satisfy them? So here I'm going to give a little example, and I'm not going to go through all the details, but the example is take a surface, say a genus 2 surface, and take a curve on that surface, gamma, and now look at the complete pre-image of gamma. And so we're going to let this curly y be the complete, or I guess components. I don't know if there are words for these exactly, but it's this entire line, components of the full pre-image. Of gamma. Okay, and now we want to define projection distances. So let's look at 3 of these. Let's say x, this one's y, and this one's z. Well, first we're going to define projections. So let pi sub x from all the things that are not x to x just be nearest point projection. Right, so z, or all of y will kind of project onto x, and all of z will project onto x. So this will be pi x of y, and this will be pi x of z. And now we define the distance to just be the diameter of the set inside of x. So the distance in x between y and z, this is going to be the diameter in x between these projections. So pi x of y union pi x of z. So what is it? It's just this dx of y. Okay, and then we can check that this satisfies the projections axioms. And this follows really from both the hyperbolic geometry and also the fact that kind of we're taking a lift of something by a discrete group. So right, the first thing you want to check is that like each of these projections are bounded, and that you can do using the fact that the group is discrete and that you're in a hyperbolic space. Great. So any question on this definition example? So now we're half the way to what a projection complex is, right? So far I've just defined this kind of set and these axioms, but now you take all this information together and you can define a projection complex. And so what is it? Well, okay, you have some family like this, you have some set and these set of distance functions, and it has some projection constant, and now just take any other constant k. Well, then the projection complex, what is it? It's a graph whose vertex set is just the points in y. And then you connect any two anytime there's nothing between them. Nothing between x and z. Right? Remember, what did I say? What's the condition for being in between? It means there's something that records a large distance. Well, what this condition here is saying is it's saying that, okay, well, you put an edge whenever you take x and z and you take any other point in your set y and they all measure a small distance. Then there's nothing between x and z, we'll connect them with an edge. Great, so this is going to give us this graph. And kind of the power of this, and we're not actually going to use this theorem, but we'll see that it has some nice intuition. The power of this and the power of this Best-Bromberg-Kudrow construction is that if this k you take to be sufficiently large, then this projection complex is a quasi-tree. So you've taken this abstract set and you've built a quasi-tree. And they use this, kind of the first application they use it for is in studying the mapping class group and proving that it has a finite asymptotic dimension. And so for us, we're really just going to use the projection complex and these axioms. We're not actually going to need that it's a quasi-tree, but I think this gives a nice intuition as to, okay, why would you think that building this quasi-tree would be useful in trying to get something like this free product out? So this kind of gives intuition, right? So if we start with this DGO setup and we want to prove something like you have this free product decomposition, well, if we had an action on a tree, then we could just apply the Basser and we'd be done. It'd be great. Well, okay, so we don't have an action here on a tree yet, but we have an action on a quasi-tree. So that might get us closer. So the intuition is kind of an action on a quasi-tree is getting closer. Again, we're not actually going to use this as a quasi-tree anywhere, but this is kind of some hand-wavy reasons as to why you might believe this is a useful thing to do. Great. Any questions on this projection complex background? Great. So now let's actually talk about how do we go from the DGO setup to the CMM setup. So we need to go from rotating to spinning. And I just want to remind everybody of the kind of some definitions of delta hyperbolicity. So we say a metric space is delta hyperbolic if all triangles are delta slim. And what does that mean? It means you take a geodesic triangle, and if you take the delta neighborhood of two of the sides, oh, I didn't make that very well, but then it contains the third side. Okay, this is what we call delta slim. So if every triangle is delta slim, you're delta hyperbolic. Or we actually make use of a different formulation of delta hyperbolicity in our paper called delta thin. And what is this? So for every geodesic triangle, you have a map to a tripod, to a tree, where all of the kind of side lengths are the right length. And what's the condition to be delta thin? It says that if you take any pre-image here, these points are within delta. And okay, there's kind of one special point in the middle. So here you have 3 points. And it turns out, okay, these are not the exact same notions, but if you satisfy one of them and you maybe just make delta a little bit bigger, you satisfy both. And this condition is kind of useful for us because it lets us say some kind of concrete things about nearest point projections between geodesics that kind of come out cleaner in this definition of delta hyperbolicity than in the delta sum. Great. So now our goal is to take the DGO setup and turn it into a projection complex. So let's just actually go through what is their setup. So again, you have a group acting by isometries on some delta hyperbolic metric space. Well, then they define a rotating family. What is it? It's this collection C, which is a subset of X. And then associated at each point in C, you have a subgroup of the stabilizer, right? And it satisfies some things. So first, to just be rotating, this set C has to be G invariant. And then we know that each of these GCs has to lie in the stabilizer of the point C. And then there's this last kind of equivariance condition that if you move by G, G sub GC is going to be the same thing as conjugating by G. Right? And this is really where the normal closure comes from. It's because you satisfy this condition, when you look at the group generated by all of these, you're actually looking at the normal closure of the GCs. Great. And then there are kind of two other conditions. So it's row separated. Again, just if all the points in C are at least row apart from each other. And then what is our definition of fairly rotating? So I kind of said it out loud. But what it says is that for all C and all G's in the corresponding groups associated at that point C, well, then if you look at any other point X in C, that's at least some distance away from C. I'm realizing now that maybe I should have called them different things than C and C, but okay, now you take any other point in your set and hit it by some element in this group G sub C. Well, what's going to happen is if you draw the geodesic between them, you pass close to C. So you pass within the one ball of C. So that's what rotating says. Great. So now from now on, we're just going to take all of these assumptions. And now there are kind of two steps. First, we just want to take this set of assumptions and we want to build a projection complex that your group acts on. And it should be built somehow out of these C's. And then we see that, okay, this fairly rotating condition, this implies the spinning condition on projection complexes. Again, I haven't said exactly what spinning is yet, but I will when it comes up.
Sorry, George, I have a quick question.
Yeah.
Can you emphasize or explain again the difference between fairly rotating and very rotating?
Yeah, so very rotating their condition is that you pass exactly through the point. They also have some other conditions on like the distances between these points that you started with, but they turn out not to really matter that much. Yeah.
Okay, thank you.
I mean, it's like barely a weaker condition are fairly rotating. Like I'm not trying to claim that it's like a broader setting really. Great, so let's look at this first step. Let's figure out how do we build a projection complex out of this information. So what do we need to do? We need to define these relative distance functions. We want to say, given any point, how do we measure the distance between other points in our set? And how are we going to do this? Well, we're going to take our point P, so imagine now we're centered at P, and we're going to just remove a ball of some fixed radius R about P. And now we're going to measure kind of the change in distance now. So we're going to look at, okay, this is maybe the distance between A and B in X originally. And then this kind of gives the distance between A and B in our new space X minus the ball. So this kind of distance here is roughly this D sub P of AB. It's this penalty you get for not being able to go near P. So in symbols, how do we define this? Well, it's just the difference between the distance in X when you subtract the ball of radius R around P minus the original distance in X. It's the penalty you pay. Okay, and we need to have R to be smaller than our separation constant. That's all this is saying. Great. So now let's kind of note some things about this metric, these metrics. So what does it mean? So dA of BC, right? What does it mean for this to be small, for this to be big, for it to be bigger than 0? Well, this is bigger than 0 exactly when every geodesic B to C intersects the ball of radius R about A. Right? I mean, if you don't intersect this ball, then this difference is just 0. Like the metric doesn't change if your geodesic doesn't. Okay, and maybe you should point out, why did we like graphs it's because in graphs, when we remove a ball, it was still a geodesic metric space. That's the only reason we restricted the graphs. Otherwise, you need to make sure that you're like a proper geodesic metric space, I think is enough. Yeah, but just, I don't really want to think about that. Just when I move a ball, it's still a geodesic metric space because I'm going to draw geodesics everywhere. Great, so if you're big, if your distance is big, and big, I just really mean bigger than 0, then every geodesic intersects this ball. Okay, and then conversely, if you're small, right, if you're less than or equal to 0, or really equal to 0, this is if and only if there's some geodesic misses the ball. So this is going to be kind of an important thing to keep in the back of your head as we check the conditions we need. All right, so we need to check these projection axioms. Okay, the first one was that it's symmetric. Here it's kind of obviously symmetric, so our original metric is symmetric. Then we also need to check the triangle inequality. And this actually turned out to be the most work. Like originally it was, we proved it had like 13 different cases, and you had to do all these little nitty gritty delta hyperbolic arguments, and it was a mess. I think now we've settled on a cleaner argument. But yeah, it's kind of the most work. And what sort of makes it hard? Well, it turns out the way I've defined this metric, it doesn't work. Right, so imagine okay, we need to just, we're always now going to be focused at a point P, right? And now we need to check that D sub P satisfy the triangle inequality. So take any other 3 points, right? And now we're looking at removing this ball. And imagine their geodesics sat like this. Right, well, this is bad because here, if we look at D sub P of AB, this is bigger than 0. But if we swap now to D sub P of A to C, this is going to be the same as D sub P of B to C, and they're all going to be 0. So the triangle inequality like immediately fails with the way I have it defined. Right, so what the challenge is we have to kind of bound this distance up here. Like when we're in this case where 2 of the geodesics miss the ball, we need to bound this. And it's going to be bounded with respect to R. Okay, and this is also true in the more general setting, right? There's also issues here. Even when all of them intersect, you still can't hope to have it satisfy the triangle inequality, at least as it's written. So here again, you need to get some handle on these lengths. Okay, so that's bad, right? I just told you something kind of false. The metric I have written doesn't work. So we need to modify it. So let's go back up. And what are we going to modify it? Well, we're going to just add some constant. So we're going to, basically the proof goes is you check, you have these different cases that are down here, and you check that you actually can bound all these distances in the right way. And then you just tack on this constant to make the triangle inequality work. And what is it? It doesn't matter so much what it is. Okay, it depends on R and delta. It is important, and I'll say later why, but this is linear in R. This will come up later. Okay, and I've named it theta kind of suggestively because it's going to satisfy the projection axioms with this constant theta. Okay, and so now what does this note mean? Really big, I just mean bigger than theta, and small, I mean less than or equal to theta. Okay, so now we need to check that this new metric satisfies the triangle inequality. And kind of the simplifying thing, how are we going to do it? Well, okay, this is too hard for me, trying to prove this metric satisfies the triangle inequality. So I'm just going to prove an easier thing satisfies the triangle inequality. So the first thing I'm going to do is define this metric where we take this difference metric and only look at it on the boundary of the ball. So this is this D sub delta B. So I'm only pulling points from the boundary. And then I'm defining the metric the same, just as the difference between these two lengths. So I'm just measuring this. So I'm just taking this metric I had and just restricting to a set where things are simple. And the lemma is that, okay, this up to some additive constant of 4R, this metric satisfies the triangle inequality when you just restrict to the boundary of the ball. Okay, and how does the proof of this work is, okay, you have to now just look at this picture. And with any triple, and you have to prove the triangle inequality. Well, what you can note, is that you look at these distances here. Well, because on the boundary of the ball, they're all bounded by 2R. Well, then also, right, I mean, the lemma follows, right? The triangle inequality for this metric follows then just from the triangle inequality for dx minus b. Right, I mean, what's our metric? It's up here. Right, well, you just, this piece satisfies the triangle inequality. This piece is always bounded. So that's where this 4R comes from. Great, so now, okay, that was very restrictive. We were on a very restrictive set that we could prove the triangle inequality. So how are we going to make it kind of work in general? Is you consider nearest point projections to the ball. So now I'm back to my general setting, and I have A, B, and C, and I want to take the nearest point projection from A to the ball, B to the ball, C to the ball. So what do? I connect A and P by a geodesic, B and P by a geodesic, C and P by a geodesic, and then I take these nearest point projections, which is the first time they intersect, A prime, B prime, C prime. And then what we do is we show that our distance d sub p of AB, well, this is comparable to this distance on the boundary between these nearest point projections. So we prove that these metrics are kind of closely equivalent. And then the triangle inequality follows. And here, this takes some work. You have to go through these different cases I showed above. And this is where we really make use of this delta. I know I've mixed it up. I think delta thin condition of delta hyperbolicity, and we use facts about how nearest point projections work in delta hyperbolic spaces. But yeah, that's kind of the general outline for how we get triangle inequality. Any questions about that? I maybe want to point something out in that, like, this is also kind of, right, this was, what did I say? This serves as kind of how do we often define projection complexes? It's you define projections first and then distances between the projections. So here it turns out the right thing to do was kind of that, right? Like these nearest point projections are the projections, and then we're measuring the distances inside. Admittedly, that was not what I thought at first when we defined these. And so I was just trying to prove it brute force, but these projection complexes really do, I think often in the background, they really are coming from some like true projections. Anyways, that was kind of some proselytizing maybe, but great. So now we need to check these other two conditions. And they're actually not too bad. So the next one is this P2, right, this in-betweenness. So we just need to check that, okay, if the projection distance at A between B and C is big, well, then when we swap to standing at B, the distance between A and C is small. Well, this is just going to follow from the thing I noted above, right? What does it mean for the distance between B and C from the perspective of A to be big? It means that a geodesic between B and C goes through this ball. Oops. Okay, and then what does it mean for the distance at B between A and C to be small? It means that we want to show that a geodesic between A and C doesn't hit the ball about B. So what we do is you basically just form this triangle, where again, you just take the nearest point on this geodesic. And now, because your triangles are thin, you know that there's a geodesic between A and C that's close to these other two. And that's how you get that the projection distance to B is small. Okay, this also relied on the fact that we were like highly separated. So you can't backtrack all the way back to B because you have the separation built in. But that's how you check this. And this last one, right, we needed to say that, okay, there's only finitely many points between any B and C. So that means that pick your B and C, there are only finitely many things that measure a large distance. Well, if you measure a large distance, right, so how this works is you just draw the geodesic between B and C. And now if you measure a large distance between B and C, it means that there's some ball of radius r about you that intersects this geodesic. Okay, now this geodesic is compact, so we can kind of get at some finite cover by these balls. Right, these are kind of all represent potential A's that could appear in this set. Okay, but then again, you use the fact that our set is separated. So you can only have finitely many things. Great, so what have we done? We've defined distance functions now on our set that satisfy the projection axioms for this data. So what does that let us do, right? That lets us build the projection complex out of it. And then because we had all these kind of equivariant conditions on G and the set C, we get also an action of our group. And remember, right, the vertices in the projection complex are exactly the points in C. So these GCs end up being subsets of vertex stabilizers now in the projection complex. So that's kind of the first half of the proof. Any questions? Great. Now let's talk about how to get spinning. First, I owe you the definition of spinning. But now that we know what a projection complex is, I can give the definition. So what is spinning? It's you start with a projection complex, you have a group acting on it. Again, now you have to every vertex in the projection complex, you associate a subset, a subgroup of the stabilizer. Okay, and then L is some constant. And so we say then that this family of all the GCs is an equivariant L spinning family. If two things, okay, an equivariance condition that is just really the same one as from the rotating. Right? And then the spinning condition. And what is this? Well, it says that, okay, now, again, if you have any two distinct vertices in your projection complex, and you take some little g in GA, so you take some little g in GA, and now you have B, and you hit B by GB. Well, now if you measure the distance in A between these two, it's big. And it's bigger than L. Okay. So it doesn't immediately maybe look like the rotating condition, but we'll see the way we defined our projection distances, it will be the equivalent. They will be equivalent. Okay, any questions about this definition? Great, so now what is the Cmm theorem? It's that, okay, if you satisfy this definition and if your L is big enough, then you get this free product structure. Something I should note is that the size of the L needed, okay, it depends only on the projection complex that you act on. So it depends linearly on the projection constant theta. Or e.g., we need L has to be bigger than some L prime for L prime growing linearly in theta. Great. So now let's see how we go from the fairly rotating to the spinning. Right, so how do we define our distance? Right. So what we want to do is we want to take some A and then take some other point B. Now this is all happening in X in the delta hyperbolic space. And then you take some G again in GA, and we hit B by G, and now we draw the geodesic between them. Right, and now what is the distance from the perspective of A between B and GB? Well, it's basically this distance. So we need to argue that this is large. Right? And this is it's not always going to be large if you just take any triple of points in your space, right? It's really, we're taking this B and we're taking this GB. Great, and now this follows just from kind of a classical delta hyperbolic fact, which is that if you avoid, so in a delta hyperbolic space, avoiding a ball kind of adds like an exponential penalty. Right, so in a delta hyperbolic space, if you avoid a ball, you have to go kind of an exponential amount of distance out of your way. Right, so what does this really say? It says that, okay, if you have any 2 points, X and Y, and you look at the geodesic between them, and now you remove some ball centered at that geodesic, well, now the distance of the path avoiding that ball is greater than or equal to 2 to the r minus 1 of a delta. Right, importantly, it grows exponentially with respect to this radius. Like, okay, but this was basically exactly the distance we needed. So putting this all together, we can prove a lemma that says that if you start with a row separated fairly rotating family, then, okay, apply this projection complex stuff to it. Well, then the new action on the projection complex is equivariant L spinning, where L grows roughly like 2 to the R. Right? This all really comes down, this all follows really from this fact. And then just putting some pieces together. Great, so how do we finish? Right? So to finish, right, if this L is large enough that we get out, then the CMM result will give us the DGO result. Right? We started with the setup of DGO, we transformed it into the setup of CMM, and then we just need to check that this L we got out was big enough. But L grows exponentially in R. And now this is why I pointed out that theta depends linearly on R. And L prime grows only linearly in R. Okay, really, L prime depends on the projection constant. Well, our projection constant depended on the R that we used. And both of those relations were linear. So we can take R big enough. Right, remember R was the size of the ball that we removed. So that L is bigger than L prime. And then we're done. We can just apply the CMM theorem. Great. And okay, this R, we need to take it a certain size. Well, you can't have R being bigger than your separation constant. So that's where this kind of restrictions on the separation comes in. And we actually get the DGO result with slightly different constants. So they needed this rho to be bigger than 200 delta. We needed our rho to be bigger than something like delta log delta plus 50 delta, roughly that. So I guess our constant is worse if delta is big, but it's better if delta is small. But I don't think it's not a big difference either way, unless you're dealing with deltas that are 10 to the 10 to the 10, which I've never encountered, but in essence, it's the same theorem. Great. Any questions on all that? A reference for what? Sorry, hi, I saw your question of reference. Okay, I'll move on and maybe we can talk at the end. So this is great. I'm just gonna take the last few minutes to just say, okay, this was half of our paper, was seeing that you can rederive the DGO result from the CMM. And then we wanted kind of a self-contained thing, so we also give a new proof of CMM. And I just want to give a rough outline of first how this theorem is proven in general, and then one of what are pieces that's a little different. So, okay, what about CMM, right? This is this condition where this is this theorem where you now are only living in a land of actions on projection complexes, and you want to conclude this free product. So the rough outline, this is very rough, is you want to recursively build up trees for your normal closure to act on. And how do you do this? You use so-called windmills, which are kind of how all these theorems work. CMM uses windmills, the idea of windmills, DGO does. I think they go back to Gromov. And I'm not really going to say what they are, but you're just kind of going to recursively build up a tree inside your space. So the question really then is, okay, how do you, there's this way to build up this object using windmills. Oh, sorry, let me say first, right? Once we're there, right, if we can recursively build up these trees, well, then we just apply this Basser theorem from the beginning to get the free product structure. So here you can really see that it's in some sense a generalization of the Basser theorem. Okay, but then the question becomes, okay, there's this construction to build windmills that I'm not telling you about, but it's some way to build things in your space. How do you prove these windmills are trees? But once you get that, then you get an action tree group on a tree with all the right properties. And so what we use that's different than what they do in CMM is we use something called canoeing paths. And these kind of go back to some basic hyperbolic geometry. So there's this theorem that I'm not sure exactly what's originally due to, but we found it in writing in this book of Epstein, Cannon, Holt, Levy, Pattison, Thurston. It might be originally due to them. But so what does it say? It says that, okay, now this is just all happening in H2. And okay, so if I hand you some angle alpha, well, then there exists some L length bigger than 0, such that what? Such that if you have a concatenation of geodesics, where at each concatenation point, you have a large angle bigger than alpha, well, then as long as these geodesics were long enough, or these geodesic segments you started with, when you concatenate all of them, the concatenation is a quasi-geodesic. So it gives you some condition on, okay, if you could glue together a bunch of geodesic segments, the end result is a quasi-geodesic. And so what do? We prove an analogous statement in the world of projection complexes. Right? Kind of part of the power of projection complexes is you kind of have a way of measuring angle, right? These projection distances can be thought of as angle. So what do we see? We say that, okay, now if you have these geodesic segments, and now these are geodesic segments in the projection complex, if the points where you glue them together have large angle, meaning that you see some point here and you see some point here, like B1 and B1 prime, then the distance, the projection distance in V1 between B1 and B1 prime is big. Right? Then that implies that your endpoints and all these midpoints are distinct, all these gluing points are distinct. Really, it basically proves that this canoeing path is embedded. Right? And that's kind of what we need to prove something's a tree. We take kind of any 2 points and path between them and see that that path has to be embedded. And so you're never going to see any leaps. And that's kind of our piece of how the proof is different. And this all follows from, there's a version of the bounded geodesic image theorem from in the world of projection complexes. And great, I'll end here. Thanks.
All right, thank you very much. Thank you. All right, you finished early. Now, if there are any questions to George, you're welcome to ask them.
Oh, hi, I just saw, yeah, so it has not been published, but it's posted on the archive. And the title of the paper is the same as the title of the talk.
Right. Okay, thank you. Any questions for George? So I actually had a question about specific. So I was trying to remember the correct intuition, how to think about this condition about rotating families, some applications and examples. So I always thought that it had to do with some kind of like a small cancellation type phenomenon, and I wanted to either confirm and deny it, because the picture I had in mind is like some sort of a cylindrical action, and we have a bunch of elements, let's say, which act alexandromically with axes which are far away, and in some sense which have like small overlaps of the axis, and then we collapse those axes to we cone them off, and they become points, right? And then the hyperbolic space to which this is being applied is this collapse space, right? Is this the kind of thing, you know, where things become rotating?
So I think so. I'll be honest, I don't.
Because I thought that there are applications of all of this to like to relatively hyperbolic groups where you know, this kind of small cancellation considerations apply. Because I think the very first examples of this phenomenon, which I remember, actually come, if I'm not mistaken, from classical small cancellation theory, where these free products as normal closures appear, right? I mean, that's what I was trying to remember, right?
Yeah, I know there are connections. I don't know the connections to small cancellation theory that well. Kind of the things that I know better are like the applications to mapping class groups.
But I think they all, I mean, if I'm not mistaken, they all come more or less from this construction that I was trying to describe, you know. So, I mean, if understood geometrically, you know, so, right?
Yeah, the way I'm used to thinking about it is more from first defining the projection complex and then getting at this. just because I've done
Yeah,
other
but,
work with these
I mean,
projections,
in the
it's very,
digital
it's
complex,
definitely not.
you don't have to have a projection complex.
No, you don't. Yeah, yeah.
A nice hyperbolic space, right?
So I think that, I mean, I think that is all true. I can't speak that well to it, because, yeah. But I know that that was the original motivation, at least behind the DGO result.
Okay.
Yeah.
All right. Thank you.
So Ilya, are you there?
Yes, who is this? Who is speaking?
This is Bob Gilman. I just wondered if you could say a little bit more about your intuition about where these things come from.
You're asking me?
Well, is that allowable?
I don't know. I mean, let's postpone this for a moment. So we can talk about this maybe like in the informal.
Okay. Okay. Sure. Okay.
Follow. So let's see if there are any other questions for George, right? So that we can. All right. If not, let's thank George again. Thank you. Okay. So now I'm going to stop the recording.